Hello viewers, welcome to my channel Chemphilic. I am Dr. Mala Das Sharma, a retired professor of St. Pius 10th Degree and PG College for Women, Hyderabad. In this video number 13, I am going to teach a few topics from photochemistry chapter by adopting a self-designed innovative teaching methodology that is teaching chemistry through riddles. Hope students will enjoy. So here is our riddle number 13. Air is a process related to absorption followed by fast emission of light. Generally, emitted light has lower frequency than absorbed light. This process can produce intense spectra. It has wide applications in biological sciences that includes DNA sequencing, gene analysis, cellular imaging and others. So this is the riddle number 13. Now let's see the questions. The primary question or question number 1 is what is referred by A? The other questions are number 2, why the process A gives intense spectra? Number 3, why the emitted light possesses lower frequency? Number 4, why the direction of electron spin is retained during the process A? Now guess for the answer of primary question. The primary question is what is referred by A? We'll see the answer. It's fluorescence. Now, this riddle is framed to discuss the following topics. Number 1, electronically excited state. Number 2, radiative and non-radiative transition. Number 3, fluorescence process. Now let's see electronically excited state, that is singlet and triplet state. Now in the ground state, generally electrons are paired up in a molecule. Now say this is the ground state and this is a pair of electron. Spin of one electron is parallel, another one is antiparallel. So total spin of these two electrons is equal to plus of minus of, that is equal to 0. That means total spin of this pair of electron is 0. Now there is another term known as spin multiplicity, which is equal to twice s plus 1, where s is the total spin of the paired electrons. So that is equal to 2 into 0 plus 1, which is equal to 1. Then the molecule is said to be in the singlet ground state. Now, after absorbing radiation, say the electrons become unpaired and one of the electron has been promoted to the higher energy electronic state without changing its spin or spin direction. That means here also it was antiparallel and in the excited state also it is antiparallel. In that case also, total spin of these two electrons are plus of minus of, that is equal to 0, and then the spin multiplicity will be twice s plus 1, that is 2 into 0 plus 1 is equal to 1, and the molecule is said to be in the singlet excited state. Now, after absorbing radiation, if the molecule goes to the higher energy electronic state by changing the electron spin, that means one electron has been promoted to the higher energy electronic state by changing its electron spin. Here it is antiparallel, say here it is parallel. In that case, the total spin of this electron and this excited electron becomes plus of, that is equal to 1. then the spin multiplicity twice s plus 1 will be equal to 2 into 1 plus 1, that is 3. The molecule is said to be triplet excited state. For every singlet excited state, there will be triplet excited state. That means for S1 there will be T1, for S2 there will be T2, etc. And one more point you have to remember, that the energy of the singlet excited state will be greater than that of the energy of the corresponding triplet excited state. That means energy of S1 will be greater than energy of T1, or energy of S2 will be greater than energy of T2, and so on. Now coming to radiative and non-radiative transitions. On absorption of light photon, electrons of the absorbing molecule may jump from S0, that is singlet ground state, to the higher singlet state, say S1, S2, S3, etc., depending upon the energy of the photon absorbed. Generally, electrons are promoted to the singlet excited state because there is no change in the spin direction. So, after absorbing the radiation, when the molecule goes to the high energy electronic state, then that is known as the activated molecule. Now, the activated molecules return to the ground state by releasing energy by the following process. What are the process? Non-radiative transition, radiative transitions. From the name itself, it is clear that non-radiative transition means during that transition, no radiation is emitted. And radiative transition means during that transition, the energy is released in the form of radiation. Now coming to Jablonski diagram. Through this diagram, you can clearly understand the radiative and non-radiative transitions. Now, this is S0, that means the singlet ground state. And within any electronic state, there will be the vibrational energy level. And within the vibrational energy level, there will be rotational energy level. So, in S0 also, there will be number of vibrational energy level, and the lowest one is known as the zero vibrational energy levels. Like that, higher electronic states, S1, S2, they also have number of vibrational energy levels within this electronic energy level. Similarly, for triplet state also, number of vibrational energy level within this electronic energy level. Now, suppose after absorbing the radiation, that electron has been promoted from the zero vibrational level of S0, that is singlet ground state, to some higher vibrational level of higher electronic singlet state. So, it has gone to higher vibrational energy level of S2. Then, from the higher vibrational level of S2, it comes back to the zero vibrational level of S2, and this difference of energy is released in the form of heat, and this process is known as the vibrational relaxation. Now, when from this higher electronic state, the electrons comes from the lower energy electronic state, say from here, that is the zero vibrational level of S2, it has come to some higher vibrational level of S1. Then this difference of energy is also released in the form of heat, that means non-radiative transition, and this phenomenon is known as this process is known as the internal conversion. So, internal conversion is the transition between the two electronic states of same spin multiplicity. That means S to S, S2 to S1, S3 to S2, whatever it is, or triplet to triplet, that is T2 to T1 or T3 to T2, etc. And this transition is non-radiative transition. Then, when the electron from this singlet excited state goes to the corresponding triplet excited state, say for example here, from the 0 vibrational level of S1, it has gone to the higher vibrational level of T1, first triplet excited state. Then also this difference of energy is released in the form of heat. And this is known as the inter-system crossing. So, inter-system crossing is the transition between the two electronic state of different spin multiplicity, that is S2T. Okay? Therefore, this vibrational relaxation, internal conversion, inter-system crossing, all these are non-radiative transitions. Now, from this 0 vibrational level of S1, when the electrons comes back to the 0 vibrational level of S0, that is singlet ground state, this difference of energy is released in the form of radiation, which is known as the fluorescence. On this radiating light, or this radiation is known as the fluorescent light. So, the transition for fluorescence is S1 to S0. Then, when these electrons from some higher vibrational level of triplet state, say from T1, comes to the 0 vibrational level of T1, then energy is released in the form of heat, that is vibrational relaxation. Then from the 0 vibrational level of T1, when it comes back to the 0 vibrational level of S0, then the energy is emitted, that is difference of this energy is emitted in the form of light or radiation, and this phenomenon is known as the phosphorescence. So, fluorescence and phosphorescence are radiative transitions. Now coming to fluorescence. Already have seen fluorescence transition is S1 to S0, and then during this transition, difference of energy between these two electronic states is released in the form of radiation, which is fluorescence process. Fluorescence light stops as soon as the light source is cut off. Fluorescence is a fast process. Lifetime is 10 to the power minus 8 seconds. It is spectroscopically allowed transition, so fluorescence gives intense spectra. Now, frequency of the fluorescence radiation is shorter than the absorbed radiation. We have seen, let us go back to the earlier slide. See, fluorescence transition is from the 0 vibrational level of S1 to 0 vibrational level of S0. Now suppose by absorbing radiation, the electron has been promoted to some higher vibrational level of S1. Then from this higher vibrational level of S1, it has to come back to the 0 vibrational level of S1, and during this transition, this difference of this energy is released in the form of heat. Then the remaining energy is released in the form of fluorescent light. That means during the transition from 0 vibrational level of S1 to 0 vibrational level of S0. So, therefore, some amount of energy is released in the form of heat during the non-radiative transition or vibrational relaxation. So, part of the absorbed light is released as non-radiative transition, that is in the form of heat during vibrational relaxation. Hence, energy of the emitted light is lower than absorbed light. Now the last point, fluorescence spectroscopy got a wide range of applications in biological sciences like environmental monitoring, clinical chemistry, DNA sequencing, gene analysis, cell identification and sorting, cellular imaging, etc. Now let us come back to the answers of the remaining question. The question number 2 was, why the process A gives intense spectra? Because it is spectroscopically allowed transition. During fluorescence, there is no change in the direction of spin and it is spectroscopically allowed, so it gives the intense spectra. Number 3, why the emitted light possesses lower frequency? Because a part of the absorbed light is released in the form of heat during vibrational relaxation. Thus, the energy of the emitted light decreases. So, energy of the emitted light or frequency of the emitted light is less than that of the absorbed light. Number 4. Why the direction of electron spin is retained during the process A? Because electronic transition involved in fluorescence is S1 to S0. That means transition between the same spin multiplicity S1 to S0. That is singlet to singlet transition which involves the retention of spin. Write your valuable comments in the comment box. Link of my previous videos on teaching chemistry through riddles is given in the description box. Watch those videos if you are yet to watch them.